This is the second video segment that I'm doing for buckling of composite laminate using the Catia's native FEA solvent. The first one was a, a laminate which was 0.25 inches thick, very thick, of course, and it was made of carbon epoxy, and all the fibers are running in the zero direction. You might say, wait a minute, laminas and pliers are a lot thinner than this. You're right, but you can think about maybe 100 laminas of the same material, same orientation, stacked on top of each other, laid up on top of each other. Then effectively you can use it for this type of problem. You can use it as a single lamina of uh, multiple values of the original thickness. So we assume that the laminate was a thickness of 0.25. Now, what we're going to do here is we're going to assume that actually we have two laminas of 0.125 thickness, which are uh, which are the skins of a foam core. So let me put this thing in the slide mode. So we have a buckling of a sandwich plate with foam core and carbon epoxy skin. This is actually drawn to scale, so it's 12 inches wide and 40 inches long. So the skins on the top and the bottom are carbon epoxy, and that yellow thing is foam. The thicknesses are, uh, this is also drawn to scale. The thickness of the foam in the middle is half an inch, and the one on top, the skins on the top and the bottom are 1/8 of an inch. Okay, so this is 4 times, the core is 4 times thicker than these skins. Now, we're going to assume that these edges, the edges of this strip, this plate, they're all simply supported, okay? And it's being compressed by a force Nx. And remember, Nx has the unit you can think about it as force, but for shell problem, you can think about it as force per unit length, okay? Now, uh, in my first video, one of the original drawings, they had a load on this side too. It was saying that compressive load on both sides, but really you don't have to draw that NX. That NX is effectively the support because these edges are all simply supported. That NX is the reaction force due to the simple support at that side. In this segment, I just deleted those red arrow, the red arrow on the right side. Okay. So here, simply support on all four sides. The simple support conditions were already given to you in the previous segment, but it's also written here for your sake. Total laminate thickness is 0.75. Remember, the 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 core is 0.5, and there are two 0.125 skins. Okay, the material properties are taken out of the East Carolina's series on hand calculations for composite design, and I'm going to assume that uh, yeah, the carbon epoxy is right here, and oops, this is not right. Oh yeah, and then so in CATIA we're going to be doing a 2D orthotropic material for carbon epoxy, and foam is 100,000 psi. It's a little bit high for foam, but that's okay. And the Poisson ratio is 0.45. So I'm going to assume that foam is an isotropic material with these two properties, and the skins are orthotropic like that. Now, um, I was going to say, because the thickness of this core is relatively large compared to the overall dimensions and also the thickness of the skin, it may be a better idea to do the core, the foam, as solid elements, but we don't have that option in CATIA for composites. So the composites in CATIA, they're all shell elements. Okay. So just keep in mind that when you put this thing together as a stacking of laminas, and later on you have to import it, you make sure that the symmetrical geometry is checked. That means it's symmetric with respect to that middle plane. Okay. Now, the calculations in that website that I mentioned, they they don't actually. Oh yeah, they do this problem, except that the the Young's modulus of their core, I think, is 10 times smaller than mine. So, but the formulas that they provide in that video segments right here also apply. So the only difference between what you see there and what I'm doing here, my foam is 10 times stiffer than what they have there. So we're going to comparing our results against these calculations, which are coming from theory. Now, this video was done on V5-6R2018, and I want to remind you that if you use earlier versions of CATIA, although the process works, but the numbers may not be, particularly as far as the stresses, which we are not interested in this particular problem. The stresses are meaningless for the present, for buckling problems. Uh, so as far as the process goes, works, but we don't have to worry about that. Okay. So let me put this thing down here. I'm going to start my CATIA program. First thing I need to do is to create my two materials. And since these are not default materials in the CATIA database, I'm going to have to create my own library. So let me kill this and start with infrastructure, material library. This first one is going to be for carbon epoxy. So I'll say carbon epoxy. Epoxy, apply. There's a name change. And then the composite has a thickness, remember those layers had the thickness of 0.125, unidirectional. Okay, apply. And then analysis, this is 2D orthotropic. For longitudinal Young's modulus is 20 e to the 6. Transverse 1.2 e to the 6. 1.2 e to the 6. Poisson ratio 0.25. Shear modulus 800,000. And the other two shear modulus 400,000. 5 zeros. And 4, 1, 2, 3, 4, 5. That's it. Apply and OK. Now we do another one. Click on it. We're going to double click on it. The name of it we're going to call foam. Okay, apply. Composite, unidirectional, and the thickness is 0.5, 0.5 inches. Thickness of the core. And analysis. Now this one is isotropic, okay? So the Young's modulus was 100,000 psi. 1, 2, 3, 4, 5. Is that 100,000? No, that's a million. Okay, that's 100,000 psi. And Poisson ratio is 0.45. And I don't need anything else, so that's good. Okay, right there, we're gonna save this thing. Desktop, my desktop, created a folder right here, buckling carbon epoxy and foam core. The material, I'm going to call this thing January 5, 6, 2018. No, 2021. Okay, January 6, 2021. Just so that I can recognize it. And we're done here. We close that. So we're going to start making our parts, our part. So click on the part. Why don't we save it right away? File, save management. This was the name of the part. Save as my desktop right there. Carbon epoxy foam core. Okay, let's make a, we need to go to generative shape design. On the XY plane, we will draw a rectangle of size 48 inches by 12 inches. So let's do this one first. This is 12 inches. And this one next. This is the length of it, 48. And we can fit it. There we are. Exit. Fill it, F-I-L-L. Join it. If you don't know why I joined, please watch the other videos. Oh yeah, and I create an axis system here. Create a point, -12 for y. The only reason I do this is that I don't want my coordinate system to be placed right there. I want it to be placed off that surface so that I can distinguish it from the surface itself. And make sure this is not current. That means that any XYZ that you discuss or specify, if anything that you need, is going to be with respect to the original coordinate system and not the current coordinate system. Say okay, save everything. We now go to the composite design. First, we create our parameters, composite parameters. Add material, my own library. On my desktop, I created this folder and I created a material right there. There's two things in it. There's the foam and there's the carbon epoxy. I need both of them. So this was the carbon epoxy, thickness of 0.125. Add the material, foam, and there is the foam, thickness of 0.5 inches. For rosette, add a rosette. Go select this thing that we created over here. I don't need it. I hide it. And then we say OK. All right, for our angles, they're all zero. These layers all have angles 0, so we don't need to create it. It's already there. Okay, now we're going to do this thing manually. So the first thing that I'm going to do is to create a plies group. Surface is right there, or support is right there. Flip it so that it. My favorite way is, draping in the upward direction, and lock plies draping direction. Very good. Okay, now we're going to create our plies one by one. There's 3 of them. Okay, so you click on the ply right there. See that ply, and it's asking you to go and select the ply group right there. And for the contour, I'm going to use that sketch. Remember I drew that rectangle. You use this. And for attributes, it's carbon epoxy, 0 degrees, and that's good. So that's going to be my first ply. You can see that it's created right there. The next one, once again, it's asking you to select the ply group right there. For the boundary or the contour, select sketch 1. For the attributes, this one is going to be foam, and the direction is still 0. Next one, and the last ply, plies group. Boundary is that sketch. And for the attributes, all you have to do is to change the material back to carbon epoxy, and you say OK. And you can always see these things here. You can stack them up on top of each other. Apply exploder, apply. There is all of them are 0. That's why they're all the same color. The distances between these things represent the relative distances between the ply. So, or the thickness of the ply. So this is 0.125. Think about it like that. This is 0.5, and this one is 0.125. I don't need this, so I just cancel it. Okay, good. So save it. We now go to the advanced meshing tools. We use the surface measure right there, surface measure. We select the surface, thick or size 1 inch. That means there's going to be roughly 12 elements in this direction and 48 in that direction. Okay, so that's fine. And then mesh it. This is roughly 500, well, it's 576 elements, so 12 times 48 is that, and exit. So it meshed it for us. So now we're going to go to generative structure analysis. If you want to see the mesh, it's right there, nothing fancy about it. Change the rendering so that you can see the edges, okay? And deactivate this mesh. All right. Now, I mentioned to you before that notice that when I have to apply loads and restraints to these edges, but right now what is blocking our view of or ability to select these edges is that there are ply sitting here, ply boundaries sitting here, and there's that sketch sitting here. So what we should do is, first of all, we should go here, right there, and hide the stacking, hide it. At least we got rid of the ply boundaries. Now, there's also sketch sitting on the periphery here. So notice that when I put the cursor there, the sketch lights up. Okay, so I'm going to hide this. Good. Now I can select the edges one by one. Okay. So let's apply. First of all, let's import our composite properties. So you click on it. It says what is the support? The support is surface. We're doing it by plies. So you go and select that ply group right there. You say OK. Symmetric, because you place it symmetrically above and below this reference surface. Now these are simply supported. We did this thing in the previous video. So these two edges, they cannot move up and down, and they cannot move in the y direction. So this is a simple support condition. Let's do the other one. This edge cannot move up and down, and it cannot move in the x direction. Simple support. Now, as far as the last one on the right side, this should be able to move in the x direction because we're pushing it. So it cannot move up and down, but it should not be prevented to move in the x direction because you're applying a force here in that direction. Okay, so now we go and apply a compressive force on that edge, okay? So, you can apply a force, distributed force, concentrated force, which is going to be distributed over. You can do it. And if you're going to do that, then remember you're applying a force. But in composite problem, generally speaking, or at least the ones that I have made, I'm applying a force, line force density. That means I'm specifying what is the force per unit length that I'm applying to this edge. Now that is minus, I'm applying a minus 1 pound lbf underscore in. Now, this is not the buckling load. To do the buckling analysis in any program, the first thing you have to do, you have to apply a static load and run it. Once you run a static problem, then you go and insert a buckling load. So there's going to be load multipliers. Whatever the load multiplier is, you have to multiply the value that you put in here, which is a dummy value really, which in my case is 1 pound. For example, if I get a load multiplier of 1,000, then I take my force that I put here, which was one pound per inch, multiplied by 1,000, and that's going to be your buckling load. Okay, so this is fine. This first step is required, but it's a dummy step because it's needed to do the buckling calculation. We're going to run it. Nothing fancy is going to happen. This is going to get compressed. That's all. And you can see that. You can see it gets compressed. There we are. Okay, so good. We need this because in order to do buckling, you need a static case solution. And we did it. It's right there. Okay, so you go now and say insert buckling case, and notice that it's expecting you to select a reference solution, static solution, and the only thing that you can pick from this tree is the static case that you ran. Static case, notice puts it there, and we say okay, and then we're going to run it. Okay, now This particular problem said number of iteration. Usually you don't get something like that, but it can happen, no problem. It says number of iterations on insufficient. Fine. You say okay. So I'm going to double click on this buckling case. It's not here. Where is it? Double click on this buckling case, and instead of 50, I'll put 100 iteration. Generally speaking, you don't run into a situation like this, but it could, and I did. So I'm going to say run all of them again, even the static one, although it was not necessary. This time I didn't get the message. So I'm going to say show me the buckle deflections. There we are. Double click on this, select the occurrences. It calculated the first 10 buckling load. Usually only the first two are important. The first one is important. And in this case, we get, it's saying that let me change the rendering here. It's easier if you see it like that. Change the rendering here to material shading. Okay, so notice that one part of it buckles down, the other part buckles up, warps out. And if you look at the occurrences, it says, all right, this is your buckling load factor. Go and multiply the load that you applied on that edge by this number. And if I do that, it's going to be 16,427. It's going to buckle in this form. So 16,427 is our estimated buckling load. So if you go to the this uh, these slides. Okay, so you look at these numbers and you see that there seems to be a substantial discrepancy between the calculations here. For example, just look at this. It looks like the critical load factor or load is 23,000. So when you compare 23,000 to 16,000, you see that the match is not as good as the previous video that I did. Now, part of that, uh, one one may be able to attribute to the fact that these calculations were based on the assumption of the classical laminate theory, where there is no shear stresses or significant shear stresses through the thickness. But when you have a thick core like that, made of foam, one may need to anticipate some issues because it's a thick plate, relatively thick plate, and in thick plates, shear deformation is important. But anyway, so it's not discouraging. However, as I pointed out, having a thickness, such a big thickness in the core, in the laminate, it may not be a uh, good assumption for doing up the shell elements. Okay, folks, so obviously these are the higher load, critical load, and of course, usually this the first few or the important one, you never get to that point, the structure fail. The other thing you should keep in mind that even if you trust this number 16,000, you might say, wait a minute, 16,000 pounds per inch. This is 12 inches. This is 12 inches. So you take 16,000 and multiply by 12 inches. That's a significant, large load that we're talking about. Yes, but remember, these are all uh, non-conservative estimates of buckling load because the, 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 the laminate may actually fail well below this buckling load due to other modes of failure, for example, either delamination or cracking, etc. So this is like the Euler buckling load that you calculate for beams. Those are non-conservative. The beam will definitely fail, not even reaching the Euler buckling load. It's an upper bound. Okay, there will be one more video segment that I'm going to be doing on buckling. However, that one is a bit more involved. It's like a fuselage of an aircraft with a window cut out in it. Basically, it's a cylindrical surface with a hole through it. Okay, have fun.